Our first session is on biomembrane. Our first speaker is Robert Nürnberg from Imperial College London. Thank you.
Okay, thanks for the introduction. I'm a numerical analyst, and my expertise is on numerical approximation of moving interface problems. And really,
Robert,
yeah?
Maybe it'd be useful for people if you had a microphone.
Or switch it on.
And turn it on.
On the help. 1, 2, 1, 2. 1, 2. Okay, it's on. Can you hear me? Yeah. So I'm a numerical analyst, and I work on numerical approximations of interface problems, moving interface problems. And really, this started about 10 years ago, together with John Barrett and Harold Garker. And when we started, we only looked at so-called geometric evolution equations, where an interface just moves driven by forces that just come from the geometry of the interface. So example flows, curvature flow and surface diffusion. And more recently, we looked at coupling interface evolutions to quantities that are determined in the bulk. So examples are, for instance, crystal growth or two-phase flow. And very recently, we also looked at dynamic biomembranes. So that means you want to look at the evolution of these vesicles, and you also account for the influence of the fluid in the background. And so I would like to give a talk on the numerical methods one can use and the kind of numerical analysis one can do. And so I partitioned the talk into two parts. In the first part, I want to talk about two-phase flow, where I highlight what kind of things you need to work on in order to couple the evolution of an interface to a fluid flow in the bulk. And that will then be the stepping stone for discussing biomembranes, which is more complicated, where the energies involved are more complicated, but you still have to deal with somehow the fluid in the bulk coupled to an interface evolution. So just the setting for the standard two-phase flow problem. So you think of there's two immiscible fluids, say a drop of oil and water, and you're interested in how the interface between these two liquids evolves in time. So I have some domain, it could be in R2 or in R3. My interface I denote as gamma of t, and then I have an interior and an exterior, and these two parts of the domain are each occupied by one of the two liquids. And so each liquid has a density and a viscosity, so the omega rho minus and rho mu minus inside, and densities rho plus and mu plus outside. On the interface, I specify normal, which I let point in the outer domain. The normal velocity of the interface, which is really what determines how the shape of the interface is going to change, I denote with this calligraphic V. And the density is because it already introduced. I also have, so in fluid problems, usually denote the velocity by U and the pressure by P. And then the symmetrized gradient of velocity is the rate of deformation tensor. And sigma is the stress tensor, where P is the pressure that we see is just the Lagrange multiplier for the incompressibility condition. And that's then the coupled problem you have to look at. You have in the two phases, in the interior phase and the exterior phase, you each solve an incompressible Navier-Stokes equation. So you have conservation of momentum and conservation of mass, which, because we've got an incompressible situation, it just boils down to the fluid being incompressible. So you've got local volume preservation. On the boundary, you can specify all sorts of boundary conditions. For the purpose of this talk, I specify no slip conditions on part of the domain and so-called free slip conditions on another part of the domain. That means that the velocity can move tangentially on parts of the container. And so this is a free boundary problem. So your interface moves in time, and the interface determines an inner phase and outer phase, and on these two different domains you have to solve Navier-Stokes equations. And in order to close this system, I somehow have to prescribe how the velocity behaves at the interface. So you need certain interface conditions on the liquid-liquid interface, and the conditions are as follows. You assume that the velocity is is continuous. So here this bracket with plus minus denotes the jump of a quantity. So the jump is 0, so that means the velocity is continuous across the interface, and it also in particular means it makes sense to talk about the trace of velocity on the interface. So that's a well-defined quantity what the velocity is on gamma. Then you've got, this is conservation of momentum, so that means that the jump in normal stress is balanced by surface tension terms. So here gamma is a constant surface tension coefficient. This kappa is my notation for mean curvature, which in my talk is just the sum of the principal curvatures, and nu is the normal. So in this talk, I only assume clean interfaces. You can also assume, you can also model situations where you've got surfactants on the interface. Then in that case, your surface tension is no longer constant, so then it depends then on the concentration of your surfactant species, and then you get extra terms here, like tangential gradients of your surface tension coefficient. And finally, the two liquids are assumed to be immiscible, and that means that the interface actually is transported with the flow. And here you note that on purpose I only look at the normal component of the fluid velocity in the exterior. So it means I haven't specified yet what happens tangentially. So I just say that the shape of the interface is determined by the normal part of the bulk velocity.
Can I ask a question?
Yeah.
If you have a gradient of or lateral gradient of surface tension along the boundary, so you probably will have tangential flow.
Yeah. So then we get like Marangoni forces in here.
No,
So
this is normal. This is in normal direction, right? And the force balance.
yeah.
Force balance in tangential direction on the interface. So if you have gradient of tension,
Yeah.
usually no compensation by any curvature term, you're supposed to have something like Marangoni flow, whatever.
Yeah.
Is it somehow taken into account?
Sorry, I can't answer this question.
Gamma is constant.
What? Gamma is not constant. He mentioned that surface
No, he
tension-
said that if a gamma was dependent upon constituted, then there would be an extra term, and he was talking about Marangoni
But
convection.
You need a whole new evolution equation, don't you, for the quantity on the surface? in that
Yes,
case.
he is.
I mean, is it taken into account somehow?
Not in this talk, but you can look at surfactants. So then you would have an evolution equation for the surfactant species.
Influence everything. I mean, if you
There
have
is no traction associated to the tangent direction. If you give a boundary, you have to look at the traction associated with that boundary, and it's only perpendicular to that, the component of the stress.
yeah, but if
So you don't have a balance there, because there is no traction being transmitted from that part of the element to the other one, unless you have elasticity at the boundary. Then you have a tangential balance.
I don't understand.
Right. So whenever you want to numerically approximate a moving interface problem, you have to decide how you represent the interface, and the same holds true for two-phase flow. And so the three main methods are phase field methods, level set, and front tracking methods. So for phase field methods, you don't represent the interface explicitly. You introduce a phase field parameter which has roughly constant values in one phase, another constant value in the other phase, and varies smoothly between these two. And then with careful asymptotic expansions, you can often prove that as your interface thickness, as your smooth interface thickness goes to 0, you actually recover the sharp interface problem. And in terms of the numeric analysis, there's only work by Fang so far who supplied the stability proof. The advantage of phase field methods is that you can use your standard PDE packages to solve a PDE in the bulk phase. You don't have to worry about tracking the interface explicitly. The downside is that the PDEs that represent your interface are very stiff, especially when your interface thickness gets small, and so it's very challenging to actually do computations in 3D. The level set method is very popular in engineering science, again because it's quite straightforward to develop solution methods. So here you describe your interface as a zero level set of a level set function, and then you transport all the level sets of the function with the right velocity. And one issue with level set methods is that in order to represent the surface tension terms, you somehow have to come up with an approximation of curvature. And what very often happens is that people take the zero level set of their level set function and try to reconstruct a more explicit representation of the interface. It could be some polyhedral representation, and then they derive curvature approximations for that representation. And the question then is, if you have to do that, then you could just take this, say, polyhedral approximation of the interface and move that directly. And that's what front tracking methods do. So they represent the interface at all times by some explicit mesh, and now move that mesh in time. So here you have to very carefully take care of the coupling between your bulk equations and the interface evolution. And so there's previous work by Bench, who looked at the one-phase problem. So there's a free capillary surface, and he provided stability proof for a nonlinear scheme. And there's also very old work by Anvedi and Tryggvason, already a long time ago, did very impressive numerical works already in 3D. So these three methods are general for any kind of interface evolution problem, in particular for when you have a flow problem. Also, the volume fluid method is quite popular, where you try to approximate the characteristic function of the interface, say, and evolve that in time. So the aim of my talk is going to be to look at front tracking methods. So I want to derive a stable front tracking methods for two-phase flow. But even once you've decided to use a front tracking method, it means you now discretize your interface directly. You still have a choice between a fitted or an unfitted method. And again, there's pros and cons. So the obvious advantage of the fitted method is that usually you've jumps in densities and viscosities, because your liquids will have different physical properties. And you also have jumps in the pressure, because the jump has to account for the surface tension effect, so there will always be a discontinuity jump at the interface. And if you have a fitted method, you get these for free in your numerical method. So you can naturally represent these jumps. The downside for the fitted method is that as your interface evolves in time, so you could, for instance, think, I will later show examples where this bubble is rising in a container. You can imagine that your mesh gets severely deformed. So if this bubble rises, then of course these will be compressed and these will be enlarged, and very often with refinement you cannot deal with that, so you actually have to remesh your bulk mesh, and that's one disadvantage. For the unfitted method, you've got a completely independent two meshes, one for the interface and one for the bulk. So you can use standard refinement and coarsening procedures in the bulk, and the main downside here is that you have to really deal with the interaction of this independent interface with your bulk quantities, which can be a bit fiddly. Okay, so when you are a numerical analyst and you want to prove certain things about the numerical approximations, very often you look at properties of the continuous problem that you then try to mimic on the discrete level. So common property is stability, so you've got some energy law, which you then try to mimic. You also can have conservation laws, which you then try to mimic. So let's just look at the energy law for the two-phase flow problem. To keep it simple, I just look at the Stokes problem. So then the conservation momentum is just the linear equation involving the stress tensor. And as usual in finite element methods, you first of all say multiply your PDE with a test function and do integration by parts. Then your terms on the boundary, on the external boundary, will disappear because of the choice of your test functions. Then on the interface, you get this term involving the jump in the normal stress, which we can evaluate from our interface conditions. So that quantity boils down to this surface tension term, and from here to here, I've just used the definition of the stress tensor, and use the fact that if you have a symmetrized gradient in a product with this non-symmetrized gradient, you still can rewrite that in this symmetric form. And so now, in the next step, I will choose the special test function u, the velocity. And then what you see is that because u is divergence free, that term will drop out. This term will be a nice guy, will be a positive term, and this term here will involve the curvature times, so nu dot u will be the normal velocity, so it's curvature times normal velocity. That actually can represent as the time derivative of surface area. And if you do that, so use the fact that this is just a transport theorem on moving interfaces. So as I said, you can represent this term as the time derivative of surface area. You finally get this expression here. So you see that the time derivative of surface area, assuming you've got no forces on the right-hand side, is monotonically decreasing, and you get the dissipation rate in terms of this term, this positive term. So that's one property of the continuous problem. The second property is that because of the incompressibility condition, the volume of the interface is preserved. And so one immediate consequence is then that if there's no forces, then circles or spheres are stationary solutions, because you cannot possibly decrease the surface area while maintaining the enclosed volume. And so one aim is to derive a numerical method which satisfies exactly these properties. And that was, for many years, that was actually an issue in engineering science, and where numerical methods did not satisfy these properties. And so what then happens is that you get so-called spurious velocities. So these are velocities that you see in your numerics, which you just know shouldn't be there, because you know that your circular bubble should just be stationary, and nothing should happen. Velocity should be zero, and just in your numerical method, you see these velocities which you know must be spurious down to discretization problems.
Question?
Yeah.
On the previous slide, it looks like you were throwing away the time dependence in the momentum equation.
Yeah, I did just to keep things simple. Otherwise, just to keep the slides less full.
Basically, stationary flows with a moving interface.
Yeah, well, it's still an evolution problem, right? It's just that your bulk problem is now quasi-stationary. Yeah. But I mean, the same thing can do for the full Navier-Stokes part. We'll just indicate that later. So, a crucial aspect of the numerical method is how to deal with curvature, and so you get this curvature term in the surface tension term, and in our works, that comes from our experience for geometric evolution equations. We always consider this identity from differential geometry, so that the Laplace-Beltrami operator applied on the identity is equal to the curvature vector. And this goes down to work by Juk in the early 90s, who used this kind of an approximation of this kind of identity for schemes forming curvature flow. And a crucial aspect in our work is to discretize the curvature independently of the normal. This is in contrast to the previous work by, say, Juk and Bench for the one-phase flow, where they discretize this quantity together. So you can think of, if you have some discrete approximation of your interface, you could just apply the discrete Laplace into your position vector, and you get a new vector, which is your curvature vector, which gives you two things in one go. It gives you the direction of a normal, of a discrete normal, and also the magnitude tells you the curvature. So that's quite a natural approach, but we prefer to do curvature and normal separately, and the reason is that it turns out that this has very beneficial properties for your mesh quality. So I just highlight this for a simple geometric evolution equations. This is surface diffusion. Doesn't really matter if you don't know much about that. It's basically it's a gradient flow that minimizes surface area while maintaining the enclosed volume. So anything spherical like here will go to a sphere, and here I show an approximation based on the curvature vector. And the downside is that then you've got no freedom in tangential direction. So that means the vertices are basically all moved in normal direction, and you can see what happens. You get a high clustering of vertices at these two ends, and if you put that to an extreme, eventually you will not be able to solve your system of equations at each time step anymore, because your system is so ill-conditioned or actually becomes singular. And in contrast to that, if you do it separately, you get a method where the vertices are naturally redistributed, so that they always stay equidistributed. And that's without any additional work. It's just inherent in the scheme. So there's an implicit tangential motion which keeps the mesh nice. And that's actually, issues with mesh quality is probably one of the main weaknesses of front tracking methods, and that's one of the reasons why in the past they weren't very successful, because people always had to worry about the mesh deforming after a few time steps, and then you have to recreate your mesh, which obviously needs time, and also you lose accuracy and so on. So
could you comment on the equivalence of the discretizations? You have two contrasting discretizations.
Yeah,
but
yeah.
with the same operator.
Yeah. So this holds true for any kind of parametric approximation of evolution equations. If you discretize this thing with the right-hand side being an unknown vector, that for reasons of balancing numbers of equations, number of unknowns, that means that in the corresponding evolution equations for the interface, you have to prescribe the full velocity of your interface, both in normal and in tangential direction. Whereas if you discretize these two things separately, you get a different approximation where you only specify the normal direction of your evolution, which gives you freedom in the tangential part. Yeah, so that's why how you deal with curvature is directly related to how much of the interface evolution you prescribe, either the full one, normal and tangential together, or just the normal.
So does that amount to do a projection on the tangential component at each step?
No, I mean the nice thing for our scheme is that this just pops out naturally from the scheme. There's nothing we've put in, and it's actually, I mean, it's a long story how we came up with that, but it's just a very lucky coincidence.
When you say discretize the curvature, there are plenty of different ways to discretize curvature in discrete differential geometry.
Yeah,
so
yeah.
What you're talking is a special one there that
So we do it variationally.
Yeah.
So you look at again, you multiply with the test function, integrate over the interface, and then you discretize that with finite elements.
Okay.
And that's because at the end of the day, you want to prove something about the schemes. So you cannot just take some ad hoc approximation of curvature and then hope to be able to prove something. So maybe I should go a bit faster now. So you can. So when you want to write down the finite element scheme, you first of all look at the weak formulation, and the weak formulation I've before already almost written down and looked at the energy law. So this is the weak formulation. Now this is the weak formulation of the conservation of momentum. Here's conservation of mass. So here you see, so these brackets are always, the round brackets are inner products in the bulk, L2 inner products. These brackets are inner products on the interface, also L2 inner products. So here you see that I only specify the normal component of the velocity should be equal to the normal component of the bulk fluid. And here's the variational approximation of curvature that I mentioned. So here's the weak formulation of the Laplace-Beltrami operator of the identity. And here you see that I separate the curvature, which is an unknown, and the normal, which is intrinsically given on the interface.
You have a
Yeah.
Do you have a continuous normal that you define, or is it?
So this is just still a continuous problem. Yeah. So I'm just that's a step in between, but I come to the discretization, I guess, in the next slide. So if you now want to discretize that, you have to introduce finite element spaces. So at any given time step, you assume that your current interface is some discrete representation of the interface. So in 2D, that will be a polygonal curve. In 3D, there will be some two-dimensional polyhedral surface made up of the unions of triangles. On these hypersurfaces, you can then introduce finite element spaces. So we only look at piecewise linear finite element spaces. And in the bulk, you just look at standard finite element approximations, finite element spaces for Navier-Stokes problems. So we mainly look at, for instance, P2, P1. So that means you look at piecewise quadratics for the pressure, and for the velocity, and piecewise linears for the pressure, which can be shown to be LVB stable, which is important if you want to show existence uniqueness for a discrete scheme, for instance. And once you've done that, then this is now the discretization. So, so several comments. This is a linear scheme. We've got a linear system of equations, and it's a coupled scheme. So you couple. So these two equations up here are basically your equations in the bulk, but you get a forcing coming from the surface tension term involving curvature. But this curvature is still the unknown, and that's why this equation is coupled to this system here. And this system is basically the evolution of the interface, which again is coupled to the velocity coming from the bulk. And you see here that the normal. I got a question about normal before. So here the normal is the true normal on your discretization. So that will be a piecewise constant discontinuous quantity. Yeah. Yeah.
Again, what was the capital V, the finite element space for the displacement?
That's just piecewise linears with 2 components in 2D and 3 components in 3D.
But
so it's vector valued.
Then the velocity is P2, and you move the interface, which is P. So you use P2 finite element to move the interface, which is P1. Is that correct?
Yeah.
Then you lose something.
Well, I don't make any claims about orders of convergence or degrees of accuracy, but you only use piecewise linears for the interface, and there's reason for why we do that. One reason is that we get these nice these meshes. That is to get these nice meshes, you have to use piecewise linears for the approximation of your interface. And we obviously use P2 elements for the velocity and the bulk because we want to have a stable approximation of the flow. But it's correct that this quantity here involves a quadratic, which we actually use that to determine the evolution of a piecewise linear function. Yeah. So our background is the evolution of interface problems. So in that case, you can just view this as the evolution of an interface gamma, which is driven by some forcing or some flow direction, which is determined independently in a bulk equation. Or if your background is more fluid dynamics, and you can think about this as a standard Stokes problem, where you get a special right-hand side forcing which comes from this interface. And what we'll see later on is that it's crucial to couple these two things to get stability. So let's just maybe quickly this what you can prove. So you can prove that if your bulk spaces for velocity and pressure satisfy this LV condition, then there's this unique solution in terms of velocity, pressure, position, and curvature. If you don't have LBB, then you can still look at this in the standard practice. Look at this reduced system where you where you basically eliminate the pressure because the pressure might be non-unique, and then you get the reduced system where you replace the full velocity space U with the space of divergence-free velocities. And then if you look back at this system, basically that term drops out. You get here only the test function involving U0, and the rest all stays the same. And if you look at that reduced system, you can prove existence and uniqueness for arbitrary element spaces for pressure and velocity. And any solution to this reduced system will satisfy the stability bound, which is the direct discrete analog to the energy law I showed you for the continuous problem. So you get that the area, surface area of the new interface is strict, assuming there's no external forces, is strictly bounded by the by the surface area of the old interface, and you get the rate of decay as well. Maybe just very quickly how you would prove that. You have to choose certain test functions in your equation. So you test the momentum equation with the discrete velocity. You test the evolution equation with the discrete curvature, and you test the curvature equation with this time step update of the interface, and then you get exactly these three equations. So this is the momentum balance equation with your test equation, the velocity. This is the evolution equation with the test function, your curvature, and this is the curvature equation with this test function here. And now you see that this term here is exactly the same as that term with the gamma, and then that term here is exactly the same as that term with a gamma times tau. And so you just add these three equations up and you get this equation here. And now in numerical analysis, that's a well-known term which you can actually rewrite as a difference of surface areas in an inequality. So we had to derive this one here, and you combine with the fact that you can bound this from below by the difference of the surface areas of these two interfaces, which you can, for instance, find in the paper by Bench. And then combining these two, you get exactly the stability bound. So that proves that our numerical method is unconditionally stable. It doesn't matter what time step types you use. It doesn't matter what the original interface looks like. You can always prove that the surface area will not increase.
So what about the forcing function f? Do you make any assumptions of that?
The forcing f?
Yeah.
Well, it can be there, and if it's there, of course, it will have an influence on your energy law. But I mean, for the purpose of the scheme, probably should be at least 2 or something. So what could happen if you have a stable scheme in this setting is that you start with an interface, and you start with a circular interface, which you know on the continuous level should be stationary, but it just happens to shrink and disappears to a point, which wouldn't violate any of the theorems I have shown you. It's stable, but it's obviously completely non-physical. And in fact, if you did that for our unfitted problem for, say, the P2, P1 spaces in the bulk, you actually would observe that a circular interface eventually shrinks to a point and disappears, which is, as I said, unphysical. So you somehow have to do some extra work to get in 2D the error preservation in. And we do that with something called XFAM. So you extend your pressure spaces by an additional function, which injects into your numerical scheme the property that the area of the faces has to be maintained. And I just show you where this breaks down in the discrete level. So here again, we use that kind of identity weight seal on the continuous levels that gives you the rate of change of the volume of the interior phase is given by the integral over the interface of your normal velocity. For piecewise linears, that's actually the same as doing what's called numeric integration, and that quantity appeared in the scheme. Now this is now a semi-discrete scheme, so we can talk about time derivatives. But this is exactly, this tick here is exactly the evolution equation in our numerical scheme for this special test function equal to 1. Yeah, then we get this identity exactly right. Now we use the divergence theorem to write it like that. And this is nothing other than the divergence of u with the test function, the characteristic phase of, with the characteristic function of the inner phase. And of course, on the continuous level, that was equal to 0 trivially, because the divergence is 0 everywhere. For discrete scheme, we enforce the divergence freeness weakly with test functions coming from your pressure space. And so unless this function is in your pressure space, you won't satisfy this identity. And for an unfitted method, the characteristic function of the interface will not be in your pressure space. If you have the fitted method and you use P0 elements, you can of course make up the characteristic function of interface just by the sums of all the elements which are in the interior phase, and you've got no problems. For the unfitted method, that's not the case, and so you have to inject that into your method, and we do that by adding a single basis function to your pressure space, which then takes care of this error preservation. And because all the extra terms in your scheme can be written in terms of integrals of your interface, we call this xfm gamma, because you just add a single extra basis function which is related to these quantities integrated over the interface. And so maybe I just skip these and just show you some results. So here that's the test case of a stationary bubble, which you know has to be stationary. If you do it without xfm, you see that you have non-zero velocities and your interface moves, and your pressures are not really nice. And this is a plot of the pressure you see. It doesn't matter whether you use P2, P1, this is P2, P0s, or you look at P1 plus P0 for the pressure. It can't really cope. And this is now with xfm, so now I plot here the continuous part of the pressure, which would be exactly 0, and this is the coefficient of the characteristic function of the interface. So really, I should have plotted a cylinder here, but it was nicer to see it like that, and then you see that you recover exactly the stationary solution. So you know that a circular interface should just be stationary, not move, and that's exactly what happens, and no matter what you take for the pressure. Okay, so this just shows you that what our method does with a very non-uniform approximations of an interface. So you see that generically our method in 2D will lead to equidistributed curves. So you never have to worry about mesh quality for your interface in 2D. And just to contrast that with a different possible approximation, I talked about discretizing this identity for the surface Laplacian of the identity in terms of a curvature vector. If you do that, you recover this so-called fluidic variant, where you prescribe the velocity of the interface in both normal and tangential direction. And this is what I've discussed so far, where you only update the normal part of velocity. So I show you now what happens if you take the full velocity. So now I put this in a shear flow. So I shear the upper plate to the right and the lower plate to the left, and that would induce a flow which in the upper part goes from left to right and the lower part goes from right to left. And of course the same flow then has an effect on your interface. So you can't see that terribly well, but what you see is that you've got vertices down here moving like this and up here moving like that, and you get this band of high density of vertices and very coarse elements up here. Hopefully you can guess that, hopefully. Which is because the vertices are moved like material on your interface with the surrounding flow. And that's this fluidic variant. Whereas in our approximation, the tangential motion is completely independent of the surrounding flow. And so what happens is that this surface just assumes the right shape, but the actual mesh changes very little and stays very nice. I mean, you can't really see that, but you can, if you're interested, you can check it on the laptop later and trust my word that these are really roughly equal-sized elements that don't change dramatically in size. Okay, I'm running short on time. So as I said before, you can do the same for Navier-Stokes, where you also do have the convective terms in there. Then the scheme is a bit more complicated. We use this antisymmetric rewrite of the additional terms in Navier-Stokes, and you can get the stability proof across as before, and also the fact that you discover exact stationary states exactly like before. So I won't discuss that much. So I also won't discuss that much. It's just some numerical issues, what you have to do. So maybe here are some. This is a 2D simulation for a rising bubble, and again, I probably skipped that. Maybe just show you in 3D. So that's so here you've got some, say, bubble of oil which has lower density than the surrounding liquid, and you introduce gravity, and then this bubble with less density just rises in this container. So that's one standard kind of benchmark problem that people look at, and Yeah.
You have about 20 minutes, so.
Yeah. So I'm better come to biomembranes. So biological membranes. I've heard that the talk after my talk is going to give a nice introduction to biomembranes. So it's a bit unfortunate I talk first, but let's just give a very quick introduction. So these membranes are built up of lipid bilayers, and these lipid molecules have a hydrophilic head and a hydrophobic tail, and if they're put in a liquid, they on their own just assemble to these lipid bilayer structures so that the hydrophilic heads pointing outwards and inwards and these tails stick together, and they form these structures. And these bilayers have properties both of an elastic solid and of a fluid. So in one sense, they resist extension, bending, and fracture. So they behave like an elastic material. But these lipids can also move freely in plane across the membrane, and so they behave like a viscous fluid. And my aim will be to discuss a model where these different properties of membranes have been incorporated, and again introduce a numerical method for which you can prove something in terms of the numerical analysis. So historically, how people looked at equilibrium states for these membranes was to look at energy methods. You define an energy for your membrane, and you do some gradient minimization methods to come up with equilibrium shapes. So I'm sure you've seen the bending energy in some of the previous talks. So here you've got the mean curvature again and Gaussian curvature. You've got bending rigidities K and K bar, and this kappa bar is a so-called spontaneous curvature. So in this talk, I will only look at surfaces of the same topology class and they're closed. So then you can ignore the Gaussian curvature term. And if you also look at the case where the membrane is symmetric with respect to inside and outside, you can set the spontaneous curvature to 0, and you end up with the standard, well-known Wilmer energy. And so if you look at energy methods for the Wilmer energy, one natural approach is to look at the L2 gradient flow. So then you set your normal velocity of the interface equal to the first variation of the Wilmer energy, which gives you so-called Wilmer flow. But for these vesicles, they're basically incompressible, so their surface area is maintained, and because of osmotic pressures, also the volume enclosed by these vesicles is also maintained. And so the appropriate gradient flow to look at in terms of finding equilibrium shapes for vesicles is to look at so-called Helfrich flow, where you also maintain surface area and volume at the same time. And the easiest way to do that is to introduce Lagrange multipliers, which make sure that these equations hold, which then maintains volume and area. And then you get a fourth order nonlinear evolution equation, which you can, for instance, approximate numerically. And that's one of those geometric evolution equations I talked about. So there's no bulk here, it's just the interface, and geometric quantity is defined on the interface. And just to quickly show you what one can do. So this is here in 2D. That just goes to this kind of biconcave shape in 2D, and similarly in 3D. So this is a method we have developed for Helfrich flow. So again, you can see that the mesh stays nice, and you get this biconcave shape. But of course, real biomembranes contain and are surrounded by fluid, and so if you're not only interested in the equilibrium shapes, but also want to look at shape transitions and what happens dynamically, you have to somehow incorporate the dynamics of the flow. And as before, there's lots of different ways you can do that. You can use phase fluid methods, level set methods, front tracking methods, and I also put here immersed boundary methods, which is a kind of front tracking method. And as far as I know, in all of these works, either the volume preservation or the surface area preservation were achieved with some kind of global Lagrange multiplier, which then ensures that these quantities are conserved. But what I want to propose in this talk is a model by Arroyo and De Simone, where the surface is actually treated as a fluid, and it's an incompressible fluid, and then you get the surface area preservation naturally, and the same, of course, for the bulk, which will again be incompressible Navier-Stokes, like in the first part of the talk. I should say that, as far as I know, there's no numerical analysis for any of these schemes so far, and the method that I want to discuss, we again can show that the method is stable and also preserves all these quantities exactly. So what is this model by Arroyo and De Simone? So they have a Navier-Stokes, incompressible Navier-Stokes inside and outside the vesicle. The membrane itself is also an incompressible fluid. So of course that then in particular gives you local surface area preservation, also global surface area preservation. And you then have to couple this system to the action that comes from the elastic energy of the membrane. So I write that as the first variation of the Wilm energy. And so what you obtain is a coupled Navier-Stokes, surface Navier-Stokes, Wilm energy system. The only numerical results for this system so far by Arroyo, De Simone, and Heltai, where they look at an axisymmetric situation where, of course, the numerics are a bit simpler because you only look at essentially a two-dimensional problem rather than a three-dimensional problem. Okay, so what are the surface Navier-Stokes equations? So if you didn't consider the membrane to be a fluid, then you can just forget about this term, and you again get that the jump in normal stress has to be balanced by forces coming from the membrane, but here these are now elastic forces from the Wilm energy. But if you include surface viscosity effects and also inertia effects, then you get this surface Navier-Stokes equation, where I will just tell you what these terms are. And of course, we are again incompressible. So here alpha is the bending rigidity. This derivative is the material derivative on the surface, which is the appropriate time derivative for an evolving interface. We've got the density for the fluid from the surface material is rho gamma. This is the surface stress tensor, which goes back to work by Busenesk and Scriven. And here, this P is a surface pressure, which you can think of as a Lagrange multiplier for the surface incompressibility. You've got now a shear viscosity, and you need these projection operators, the projection operator for the tangent space to make the surface stress tensor well defined, and you also have the surface rate of deformation tensor similar to the bulk rate of deformation tensor. And this surface Navier-Stokes now have to couple to the bulk Navier-Stokes, and that's similarly to the two-phase flow problem I discussed initially. So we've got the incompressible Navier-Stokes in the bulk with possible boundary conditions. And again, to close the system, now you have to describe conditions on the interface. So again, the velocity will be continuous. We've got this coupling now for the momentum conservation. We've got local preservation of area, so surface incompressibility, and the interface is again moved in normal direction by the velocity coming from the fluid. So up to now, I've discussed the advantages of the approach where you only specify the normal velocity of the fluid. And now we'll take a step back and actually say that for this problem, you can actually use the approach originally devised by Juk, where you use the full curvature vector, and which goes hand in hand with prescribing the full velocity of the interface. And why is that? That's because the bulk fluid is incompressible on the surface. And that means you get local surface area preservation. And for a discrete method, that means, for instance, if you were using P0 elements for the weak approximation of the surface incompressibility condition, that means that the area of an element will never change in time. And similarly, the length of a segment in 1D will never change in time. So of course, if you start with something which is, say, equidistributed, the weak approximation of this quantity will give you for free, if you use the full flow, that the approximation will remain equidistributed throughout. And so there's nothing to be gained for looking at only the normal equations. We actually use the much simpler scheme, which uses the full velocity, similarly to what Juk did. And if you do that, you can also use this work by Juk on the stable approximation of Wilmore flow, because at the end of the day, we want to prove, again, a stability bound. And so we somehow have to couple a stable approximation of the evolution of the interface with the quantities in the bulk. So maybe just quickly, this is just, again, I just did the Stokes version to keep things simple. Otherwise, you've got loads more inertia terms in here. So we see the momentum equation now has this additional term involving the surface viscosity. You've got the surface pressure, which ensures local area preservation on the interface. And this is the term coming from the Wilmore energy, which in weak form can be written like that. And this is the, once discretized, is the stable approximation that Juk came up with 7 years ago. And you see that now here I've actually prescribed the full velocity of the interface. Similarly to the two-phase flow, you can show energy laws for the continuous problem. So you can show that the Wilmore energy, if there's no external forcing, no boundary conditions, so just note the boundary conditions, then your Wilmore energy will actually decrease, and you get the right rate of decay. You also have conservation of area, of volume, enclosed volume, and conservation of surface area. And we can now introduce a discretization that mimics all these three properties. So stability we just get by combining the ideas I showed you in the first talk with the stability result from Juk for Wilmore flow. The surface area conservation you get basically for free if you just use the weak approximation of the surface incompressibility and use properties from the evolving surface finite element method, which you can find, for instance, in this paper by Juk and Elliott. And the volume conservation is a bit more involved than before, but I think I spare you the details. It's about something like virtual elements. And this is then the scheme just for the Stokes part. And then, yeah, maybe it looks a bit complicated, but it's similar to the two-phase flow problem. We've got the equations in the bulk, which are now, so this term is the forcing from the Wilmore energy. So that's again on the new time level. So again, this is coupled now to the equation on the surface, where this forcing is determined in terms of the curvature and the shape of the current interface. And here you see that I update the interface both in tangential and in normal direction. So maybe just some numerics towards the end. So this shows you the influence of inertia. So in this case, I have no inertia terms on the interface. So the fluid only has viscous terms. And then this thing just relaxes to its energy minimizing shape, which for this reduced area turns out to be like that. Whereas if you have inertia terms present, this thing will wobble a bit first and then settle down at the minimal state. And then what people are interested in is to look at vesicles in shear flow, and there's two important regimes of motion. One is called tank trading, when the vesicle assumes a stable shape, a steady state shape in the flow, and the material is just circulating around the interface, and that you can see here. So, oops. Oh, okay, sorry, that's tank trading. Okay, so on the left you see the interface, on the right you also see the bulk mesh, and you see now that this is a stable shape, but the velocity goes around like that, and also the surface fluid moves around like that. That's called tank threading for obvious reasons, and there's also tumbling, and this is so I think this is when the surface viscosity is sufficiently large, then that it can't assume this tank threading shape, so it actually is forced to have this tumbling motion and change around. So I think okay, there's one more
Question?
Yeah.
What sort of initial data do you need to get that solution? Or is that a global attractor of the dynamics?
So for the tumbling, or so the critical parameters are the so-called reduced volume, and the if you have it, the viscosity contrast in the bulk, which are here set to 0, and the size of your surface viscosity, and depending on these three parameters, you then get either the tumbling or the tank threading motion. So the initial data is irrelevant. It's just the reduced areas. It's scale invariant relationship between surface area and enclosed volume.
So for a single set of parameters, the right combination, you have a single attractor.
Yeah. And so that's in 3D. You have a Poiseuille type Stokes flow, so you can't really see the domain, unfortunately. So it's basically a big box here, and then there's a constriction, and then there's a bigger box at the back, and you force these four. So there's a flow, an incoming flow like that. So these 4 vesicles are forced through that, and so you see there's this constriction, and then here they will come out again, and you can see how they evolve that. Okay, so I think my time's up, and I'm done. Thank you. Oh, that's a question?
I mean, this is very beautiful. Is there any way to introduce fluctuations? I mean, you could use the Navier-Stokes fluctuating Navier-Stokes equation. Would that be very hard?
So you want to introduce some random noise, some stochasticity?
I mean, it's known that the fluctuations will change the tumbling, the tank threading, phase diagrams.
Yeah.
So fluctuations are important in this system. And my question is, can you introduce this into your...
Well, I mean, I have to say we're extremely glad to be able to, I mean, our focus is on numeric analysis, and to actually be able to approximate this very difficult coupled problem and still be able to prove something, it's an achievement. Of course, now you can think of adding certain physical effects on there, but then probably will be very difficult to prove something about the numerical approximation you get. But I mean, I showed a slide with lots of different numerical methods, and I'm sure there's other methods where you can add stochastic terms as well, so it's not just unique to ours.
Just out of interest, how long does it take to simulate that final simulation?
So this one maybe 3-4 days.
So it looks like a red blood cell, but it's not a good model for that.
Yeah.
There's no internal structure to it.
Exactly, yeah. So I mean, that's something I learned.
The red blood cell in this kind of geometry would be extremely relevant. I mean, people use that for malaria and things like that.
And you need some
diagnosis, but you do need that.
It's a cytoskeleton or something, right? So I mean, I don't even know how that would influence the equations. So.
2 questions. One, concerning the membranes. You considered, you modeled the membrane as one layer, right?
Yeah.
There are 2 layers, as far as I remember. The friction between 2 of them is more important than interaction with water, with outside medium, simply because the friction coefficient is larger than the effective friction coefficient with the bulk. How would it? Did you take it into account, or try to take it into account? Because there were calculations of, for example, of tether pulling out of the membrane, where this relative motion of 2 monolayers was the major factor, basically, determining the dynamics of first, and second, of course, application to real cells would require introduction of lateral shear modulus, which is not there.
Yeah,
Due to
so,
cytoskeleton, due to membrane skeleton in the case of red blood cells.
so all the numerical methods I discussed here and cited all treat the vesicle as a single monolayer, as a single sharp interface.
Question:
But,
what would be the effect of?
it's true that if you want to
in
be
order to be able to apply it to dynamics of real membranes, I think it would be necessary. Also, a third short question. You probably assumed something concerning the numerical values of the membrane viscosity, of the bulk viscosity, relationship between them. How important, how relevant is at all the bulk viscosity of water? I used to think that it's in most cases it's nearly negligible as compared to internal flow of the membrane and the friction within the membrane.
Oh, that's interesting to know. I mean, if you look at engineering literature on dynamic vesicles in shear flow, there's tons of papers where they look at phase diagrams, how the viscosity contrast in the bulk influences the tank treading, tumbling, and in 3D also get a trembling motion in between. They always look at the viscosity contrast in the bulk as the driving mechanism. And obviously, we discovered that in our numerics, you can have no viscosity contrast in the bulk, and just the surface viscosity will trigger the transition.
I think if you would put realistic numbers, you would probably see that this is a reasonable explanation.
Okay.
But one has to check it, of course.
Okay.
We can continue in the group discussion. We can continue the discussion. When do you want us to be back, Matthias?
It's quarter to.
A quarter to?
Yeah.
Okay. Then see you.
That's the
Thank you
time.
very much. It's amazing, isn't it?